Good morning, everyone. Thank you so much for attending today's presentation. This is Monday morning, so people are coming in late. That's okay. So we will start right now. My name is Levi. I'm a technical director of the branch. Today is an architecture and institute session, and we have the first speaker here. And then today's moderator will be Ashin, is our AI trainer.
Thank you, Deontay. Good morning, everybody. Thank you for being here. We've got ample people here, and we also have 18 people online. Welcome to all. As Deontay mentioned, today is going to be the AEI presentation. AEI, for those who don't know, is Architectural Engineering Institute, and the Dallas branch of AEI is actually formed pretty recently. At the end of 2025, the first session was on the DFW Airport extension, which was our second AEI technical session. At the national level, it's been around from the 90s, but in Texas, we're expanding recently. So today, we're very happy and fortunate to bring both architects and engineers in the same room to talk about the Northwest ISD new 730,000 square feet campus on 138 acres in the Northeast Fort Worth. The project brings together academics, fine arts, athletics, outdoor activities, and collaborative areas into one cohesive future ready. Let me quickly introduce the speakers. We have Levi Swinney, is an associate partner and a senior project architect at Blair and Partners. He has 20 years of experience in K-12 and higher education design, working on projects ranging from renovations to large new high school campuses. Levi brings strong experience in planning, schematic design, quality control, consultant coordination, and construction administration. His work focuses on creating thoughtful educational environment that supports students, teachers, and the larger community. Our second speaker, Patrick Glenn, is a partner and managing principal at Glenn and Partners. Patrick has 30 years of experience in educational planning and design across Texas. He has completed nearly 235 projects representing more than $3 billion in construction for over 50 school clients. His portfolio includes award-winning projects such as Amy Porter Riverside High School, Hawthorne Elementary School, Washington Middle School, and J.J. Pierce High School. Patrick has also received more than 60 design awards, including multiple ALEP honors, and is widely recognized for his leadership in educational facility design. Our third speaker, Stephen Blair, is an associate principal at Alpha Consulting Engineers. He has more than 12 years of structural engineering experience with a strong focus on K-12 educational facilities across Texas. His work includes new construction, renovations, additions, and complex projects on active school campuses. Stephen provides project coordination, technical oversight, quality assurance from design and construction, helping them with practical and efficient structural solutions. And our fourth speaker, Jared Boyles, is principal at Alpha Consulting Engineers with over a decade of structural engineering experience in Dallas-Fort Worth area. His background includes educational, commercial, healthcare, and institutional projects, with particular experience in higher education and storm center design. Jared brings a well-rounded perspective of construction architecture and engineering, allowing him to support efficient and well-coordinated structural design. With that, let's put our hands together and welcome our speakers today.
Well, good morning, everybody. My name is Patrick Glenn. I'm the architect at Glenn Partners, and I'm not going to talk a lot today. The project's actually going to speak for itself. It's an amazing project. We couldn't do projects like this without Jared and Stephen and their firm, Alpha Consulting Engineers. We've pushed them quite a bit architecturally, and I think you'll see that in the presentation. There's a lot of stuff that's written up on the screen, and I'm not going to sit here and read it to you just for brevity of time. I'm just going to go right into the design team. I think we had wonderful introduction this morning. Again, my name is Patrick. This is Levi, Stephen, and Jared. And all I want to do is just highlight a couple of things as it relates to project numbers. So 795,000 square feet in this high school, all on one campus, which is pretty absurd. It's on 128 acres. These 128 acres slope about 75 feet across the site. So there's a lot of split levels throughout the design. $465 million. 145 classrooms. In fact, I counted these yesterday. It was actually 146. But and then those 146 classrooms serve 3,200 students when this high school gets fully built out. There's 4 distinct learning houses with 4 different outdoor courtyards that support those. 7,500 seats stadium, a 1,200 seat theater. I think that there's an arena that seats about 3,500. It's like I said, it's just over the top on every complete element of the project. So I'm going to stop talking. I'm going to let Levi and Jared and Stephen actually show you all the details.
So we'll start off kind of with our site analysis. I'll try to keep this brief. This star located is actually like where our site is. It's right up near Alliance Airport, right across the highway from it. So you can see Alliance kind of highlighted here in red. Our site's that little blue triangle there next to the color ID map. So this is actually on the boundary of the Northwest District. Probably one of the most challenging sites I've ever worked on. Again, you know, as Patrick mentioned, there's like 75 feet of fall on this site. It's not flat. It's not square. It has a few easements that you can see running through it on the left. I say that sarcastically. There's a lot of easements running through this that made it really challenged to cite everything on the project and all the program elements. To just hit a couple of highlights here. There's, what do we got? 83 borings on the geotech. I think we've got over 8,000 feet of retaining walls on the site, which that was a record for me. It's a lot. Subgrade zones, we did slab on grade and slab on void. There's different elements to that. Almost 3,000 piers. I feel like we could have got there, but you know, back just a little bit. Just under, or just over 4,500 tons of steel. And our spine corridor length, which we'll get into the plan, is over 1,100 feet long. So it's a pretty massive undertaking. It's like we'll see. Our design concept, we kind of started with looking at the airport in our context of where we were, a concourse versus terminals kind of theme. So you can kind of see our main spine. We treat it as the concourse. So it'd be like the orange hallway kind of running north-south. And then all of our classroom wings kind of follow that ribbon in yellow. And they're kind of terminals plugged in. So each learning house has its own floor. Some elements are 2 stories, some elements are 3 stories. And at the facade fenestration points, we kind of looked at runway striping, and that's how we kind of dealt with like the speed and acceleration of planes taking off, and that kind of informed our language for the fenestration on the facade. So here's our site plan as it is completed. So you can see we had a lot of things that fit in there. We actually did a little bit of a land swap on this to get everything to fit. But we really had to do a lot of work to make everything work around the easements and whatnot on the site. It's got full baseball, softball, practice fields, a stadium, wetlands, a pond. We're going to end up with an ag facility on the northeast corner that's under design right now. So lots of elements. Floor plan, this is kind of basically just to orient you on this. We'll look at this here in a few slides here in the future, but our entryway, our main entry is here off the east side off of Riverside Drive. That main spine runs north and south, so there's parent and for student drop off on either the north or the south end, and then we have all of our main services and utilities coming into this interior fire lane here. So that's like our kitchen and main electrical service. Arenas down here, theaters up on this end, and then the classrooms kind of undulate around that with the stadium kind of being wrapped around by the entirety of the building and program. So on that note.
Levi, Patrick. So my name is Jared, consultant, the EOR on this project. So it's kind of hard to tell here because the screen's a little pixelated, but this is how we started laying everything out. This is the dimensional control plane. We ended up with 3 different work points for the corridors, because it's kind of like this undulating ribbon that goes down and intersects the spine. We tried to keep everything as practical as possible, so all the degrees, all turns on were about 12 degrees each. And we had to figure out all of the brick coursing, so every angle, curve, I figured tangents and all that, to get it all in increments of 8, or as close as we could to it. This is our lateral system plan, so all the different lateral systems that we use throughout the building. So the red are shear walls, so CMU or ICF, concrete shear walls. The green are moment frames, so all the way down the spine in the middle. We have moment frames, 30 to 40 feet on center. Vertical braces are important, which are a little difficult to see, but they're scattered throughout. And expansion joints are in the loop, so we have this segment this building because it's so big. I think we ended up with like 14 different structural buildings based on all of the expansion joints. So this is, I think this is pretty cool because this is their first hand sketch of what the facade and exterior would look like. So you can kind of see the spine running through the middle, and then the ribbon, the academic corridors that go out through everywhere. So we have a video, I'm not sure if it's going to play or not, but basically it's making fun of artworks. There's a doodling like this, and then we got to make it all work. So then it comes to the contractor, and he's like, yeah, what's the cost for this? Well, we didn't tell you the cost. And then it gets to the fabricator, and goes, what? What is this? So even in design, I mean, we had to talk with the contractor and fabricator and make sure everything would work because we're doing some pretty crazy stuff. Okay, yeah. Anyway. So from that sketch, this is the SketchUp model that was produced. And it gets pretty close to what the final product becomes. So there's the rendering from the SketchUp model. And then from there, we bring it into Revit for our designs. That's the structural Revit model. So it's still pretty close to the original. You can see all the retaining walls everywhere. You know, back here for baseball and following that easement that goes across there. There's a pond down here, so cables for that, and all these landscaping terraces. Things like. So there's the construction photo from where we are. That was taken this morning, actually. So that's how it stands today. So there's a lot of things that we could talk about, and we're going to keep this brief for 30 minutes. So we kind of focused on 3 areas throughout the project. But there's a lot of honorable mentions and all the cantilevers. We call them up and top. That's the first floor is one side, the second floor is that side, third floor. Just keeps on going. The majority of all of the corners in this building are curved. Figure out how to cantilever in curve multiple times. That was fun. There's transfer beams all over because the classrooms above don't line up with the classrooms below. So to extend some beams out sometimes. 3 times.
Feeling a lot of heat.
Still too easy.
On a lot of blame.
There's a lot of tight tension spaces to make sure that MEP fits in there. So one of our trademarks, I would say, is they have to have this perimeter in that wraps all the way around each floor, so you know where you are. Kind of a signature thing, and trying to get all that to fit with all the transfers and all that stuff. It's challenging, but we'll stick to these 3 for today. So the first one is the main corridor, the second one will be cafeteria stairs, and third will be the theater. So this is a rendering I showed a client earlier for the main corridor. So this is the spine that runs all the way down, and a couple of these grand stairs can go across each level. You can see this side here, there's nothing behind there, so that's just cantilevering off of this column. Down here, we were fortunate to get 2 columns, but up here, that would block all of the views, so couldn't have that. This here is what it looks like today. So it's pretty close to what the rendering was. Let's see. So this is how we got it to work on the nuts and bolts. So on level 1, we, like I said, had the The 2 columns down here, but on level 2 to 3, we wanted this to be open so you can have nice views all the way across that spine. So when you stand on one end, you say it's over 1,100 feet long, you can basically see the curvature on this thing. And there's no columns, this full way. It's just these little finger beams that stick out. And from the column to the edge of that is about 14 feet, I believe. So getting that to work with vibration, all students walking through there, and it was a feat. So this was kind of 2 weeks, one week. Okay, so that required a 2-hour fire rate install structure. And we ended up going with steel columns that are filled with concrete for the fire rating. And then for this main corridor, we use these monoframes all the way through. So they're basically composite columns, steel and concrete. These over here are recent model iterations to try to get this to work. I think we had around like 20 or so. I know I found one of them at the building code. So this is the one we went with. So here's kind of a blow up of what that finger beam looks like. We had to taper it in here so that all the mechanical equipment was fit inside here, like fire sprinklers, all of that. Yeah, there's a lot that went into this, but another thing how we work hand in hand is making sure all the columns were consistent in all the areas. So all the way down the spine, we make sure that they're the same size each time. So we found the worst case, and we've ended up going with 18 inches, 18 inches, and 30. That's one. So here's some. There it's hugging the columns. So this is an 18-inch diameter column. This is a 30-inch diameter column. And here's a photo of people walking around this corridor. Nothing but fun. Pretty cool. I could talk on this for days, but I'll try to keep it concise. This is the second focus area. This is the cafeteria. So this is a rendering. And what's to ask? Does anybody see anything that kind of defies physics in this screen? Structural glass. Yeah, structural glass. That's one here. We hold up this floating hat. Yeah, so that's here's the one meme. Architect letting to show some crazy renderings to the client. Saying keep quiet. Good. So this is where we're at right now. So it's pretty close, as you can see. There's only 4 columns, pretty big columns, granted, but going down that corridor, they look like that. So one of the second big challenges on this project was getting this landing right here to work. So as you can see, there's only 1 column that goes all the way up back here, but this whole thing is floating up here. So here's another view of that. So if you're standing underneath it, this is cantilevered about 23 feet, something like that. And that's hard to see, but the ceiling is right next to this beam underneath. And then it comes down, bulkhead, and it goes this way. So we added a little kicker and tapered this beam right here. And this is supporting all of that floor back here, all the way to that column. So even at the column, it's cantilevering out quite a bit. So I had a couple of sleepless nights on that, but it works. So, yeah. And I'll hand it over to Steve later.
Well, thank you. So for this picture, we actually had to go into 2027 when the building's complete, and we got a picture of me there and back here, put it in the presentation. Because that's what it's going to look like, but obviously it doesn't look like that now. So as you can imagine, a project this big requires an army. So obviously Jared is working on a portion of the building. We had another guy in our office, Caleb, working on the academics. And one of the areas I worked on was the auditorium, which was definitely a big learning curve. And beyond that, I would say that the majority of our office, about 25, worked on this project. Because even with something like this, if I'm taking a third of the building, I can, So the auditorium here, this has about a capacity of 1,500 people. When it's complete, you can see I'm standing on the stage, virtually. And the stage itself, if you go up to the roof, is about 80 feet tall. And that has to do with fire curtain requirements. Once you get a certain height, you need a fire curtain that can raise the full height of the stage and proscenium go above the stage, and then you have a fly box above that, and then you have your roof above it. So in total, we're right around a little under 80 feet. So this is the tallest part of the project that's right above me in this image. You can see that we have a balcony that kind of does the U shape at the second level that we also have the frame out. So here you see all the finishes, the ceiling tiles, the acoustic panels. If you want to learn a lot about acoustics, you know, you never thought you would in your life, one time in Victoria, because we work with a really great leader consultant, HW, who does this all the time, and leaned on them heavily to help guide us. Quick image of the Revit model. So this is all the skin removed. You can see on the ground level, we have the orchestra pit. That's not really, you can't really see it, but there's like a 9-foot deep pit for the orchestra, which is basically a basement level. And then we have concrete on geofoam blocks, which forms the seating and the steps as you go up. Very similar to what a lot of movie theaters do. And then at the second level, we have the framing, steel framing for the balcony. And the balcony itself had 2 different tiers. This is looking from looking at the balcony framing. This is maybe back in April, I believe, when we did a site visit out to the project with our office. Here's some of the balcony framing up there. So I'll give a better image of that in a second. But obviously, there's a whole lot of shoring that has to go in for these very tall walls. And we have, you can see steel columns that are integrated in between. And so basically, even though the columns are doing all the work for gravity, we did tie them together to the walls, mainly so that they would move together for lateral gravity reference separate. Here's an image of the Revit model for just the balcony portion. We felt like this would be helpful for the contractor to see because there was a lot going on. Just looking at this 3D plan, there's a whole lot of text that gets very confusing very quickly. Here's an image of the current construction, or I said very recent. This is just one 2D image of a frame from our recent model that we use. So we used Ram Structure System for designing our composite steel beams. But if you're familiar with how the design goes, once you hit negative moment, then they can't be composite anymore. So with these cantilevers here to form the balcony, these had to be designed, in reset with not accounting for composite effects. With all the weight from the concrete, the superimposed dead load, the superimposed live load, and obviously deflection was a big thing here. So we have a cantilever and then another cantilever. And so we have 4 different of these frames, and this is what you're not going to see when you have all the step seating on top of it. Basically, what we wanted to do was limit this deflection here. One way we did that was there's a big text up here that I know you can't read, but it basically says, hey, make sure you fabricate this beam with a tip in curvature upward about 3/4 of an inch. And that allowed them to not have to shore this beam when they pour concrete. And then also we wanted to make sure that we got the load ultimately up to the roof. There's a roof deck here that you can't see. We wanted to make sure that we got it up to the diagram as quickly as possible. There it is.
Okay, so this is just the renderings versus the construction progress. We can see what the initial ideas were and how close they became to reality as of today. So this is the main entry, the east side. The main academic wings here and science classroom back here. But again, I mean, just looking at renderings, you can see how thin this band is that goes all the way around. Cantilevering. So that's the actual construction right now. So we really had to work hand in hand with one partner and the MEP as well, just to get everything to fit within these plans and still keep that band. I think the band was like 2 foot deep. So all of these beams across here are 14 inches deep. And then you can see barely the roof drains that come down, go inside these columns. Out. So here's the science entry, same kind of thing. This is looking back at the data here. This is where we're standing right now. So cantilevers over here. See all those things protruding out there. Like Steve was talking about the steel integrated into the CMU. Here's the fly loft back here, or behind the stage. This is a view of the media center because they don't do libraries anymore. So, gone are books in their iPads. So it's pretty open. This is a learning stair here. This view is standing over here. This guy is looking out. So it's pretty close to what the rendering was. City learning stair. Here is the arena. You can enter on level 2 and then it dips down to a level on all 4 sides. See these trestles up here. Here's a similar shot structure and kind of a panoramic view. So like, so they had to leave a big section out to get all these cranes to come in and erect all these space trusses up here. So these trusses, trying to get a scale figure in there. Those are about 14 feet deep and it's about 150 feet. Here's a photo from the stadium press box, the concourse level, just looking back at the building. So here's that arena, the academic portions. That's the visitor seating. Back on this side is an indoor practice facility, range building. Here's the site right now. So all the CMU walls are up in this stadium, and my main focus is on the academic portion. And here's the spine that runs all the way down the whole thing. These areas have not been constructed yet, but they are the pergolas, the service shade structures as you walk into the arena and stadium. So here's the arena and stadium over here, and the field will be sunk down that side. Here's another view on the other side of the arena. So here's the arena. It's a bridge right here that has all locker rooms and coaches' offices, I think. And then walk down to the field over here. So that is the project. Anybody have any questions or anything?
First the tornado shelter.
Oh, good question. It is the student for this, so it's on the southwest side. Here, find the overall. It is right there. Good question.
Do you experience any variations in your city level drawings during the fabrication process?
City level drawings.
From the construction document level drawings to the fabrication level?
Oh,
Have you experienced any structural breakages?
yes. Every sheet had a cloud on it.
Huh?
Every sheet on the chalk marks had a cloud on it. But yeah, we did quite a bit. One example of that is we're looking at this corridor. So these columns that are 30-inch rounds, they don't make those in that grade of steel that we reflect. And so we gave a little detail of what our academic brains thought if we could come up with some headed studs on the inside to engage in concrete. And it's also 8 ESS3, so architecture exposed steel level 3. So it has to be almost perfect. So they said that's not possible. So then we had to work with the fabricator to make that possible. So we ended up using a different grade of steel for these, and they drilled through and they drew rods to service the studs, and plug over the outside. So it all looks good. So yeah, we work hand in hand with the fabricator a lot.
Follow-up question, mine. Any connection detailing affected the actual design at the end of the day?
Yes and no. There were some where with scheduling and everything, we maybe miscalculated once or twice on like transfer beam or something like that. And so we had to say, hey, the connection engineer, we gotta look at the connections, say, we can't get this to work. So we say, well, this is what we need to happen. Let's take a deeper look at this. And again, we maybe had to add a kicker here and there, something like that.
Okay, thank you.
The erection sequence had to be completely rethought after the drawings were complete as well. Because it's right next to Alliance Airport, and there are some height limitations on cranes, so they had to do more cranes, but lower cranes. Erection sequence had to be completely rethought. So
They used the 3 different cranes to set those trusses across the arena, so because they were so strapped for crane height, so that it really has been a Getting everything right.
I think the FAA actually came out on site, setting regulations for their cranes. Yeah.
I see, lots of stairs. What about your accessibility?
There are
Elevators did y'all have?
7 or 8 elevators on the, so two in the stadium, sorry, there's two in the press box. So I have one, these breaks. And then there's one in the arena, one near the practice gyms, one in the main building, one in the theater, and then one in the digital practices. So there's accessible access to every level. And even the entry sequence, like coming into the stadium on either the home and the visitor side, have extensive ramps that we can really locate up and go. There's ramps to get down, so you got a lot of area to work with on site.
Great presentation, all. Thank you so much. My question was, given the very innovative design you guys have come up with, working with the engineers and with all the school board and all, how have you incorporated physical security? Standpoint and making sure that it's safe on campus, because that's a big concern everyone has these days.
Each district kind of has their own standards for how they do that. We don't get to like publicize all of their strategies. But they do, this school has instances of bullet resistant films and glazing portions. We do have a lot of glass. But they treat mostly the main entry points. There's also a good amount of fencing on this as well. And another thing that we kind of, not just for classroom lighting, but those interior corridors give kids safe spaces that are within the envelope of the structure. They can go outside, learn outside, and not have to be outside of kind of the physical threat barrier, because the skin on this alone, I mean, there's a ton of potential entry points. So they have to kind of strategize each entry. So
Thank you. Big revolution. So we mentioned about 8,000 feet of beginning was so what kind of beginning was to be placed there? What drove the decision on the kind of beginning?
All of them. Yeah, all
all
of them. See if we can go back here. So on the site plan. Yeah, so those red lines on the right side, those are all retained. So we had modular block walls that civil handles over here on. This side right here, I think that's the distance from the track. Practice fields. That was some of the larger retaining walls we had. I think they were so we actually had buttresses on the back side for those. The majority of them were just cast in place concrete walls, great beams and piers and heavy pier downs and such forces. We use redraining backfill for the majority of them with the pressure drain. Use those pressures. What the actual pressure not to do.
Hold the village on the floors.
Explode concrete. Was supposed to.
I have a question. So what type of contracting method was used? Like, was it design bid build? Was it progressive design build?
Yeah.
Can you talk about the canopy for the stadium?
Sure.
Is it, curious, is it PVC, PTFE, any variation of it?
It's if you're talking like the fertile elements and like you do have a cantilever roof structure, kind of out over, because why not, for cantilever and everything else. When you look at the stadium, it definitely has an eyebrow on it. That steel structure, we've got a metal soffit panel on the bottom, and then it's a single ply roofing membrane above most of that. So it's
rigid.
It's rigid.
Okay, from the rendering, I thought it was like flexible. This time.
That's cool. Maybe we'll look at some of that, maybe push it a little bit further, but now, yeah, it's all rigid.
Okay.
All jokes aside about how crazy or stupid we were, a project like this just does not come around. It's like a once in a generation project. So when you have a project like that, you don't try to hit a single, try to hit a home run. And that's why there's all these crazy elements that you see in the project. And Jared and Steven and their team at Alpha just were absolutely amazing on trying to make all of those crazy ideas come to life. Aaron, which she's not here today, but one of the project designers, and I were walking through the facility about 2 weeks ago. And I literally stopped and said, I cannot believe it's land. That's it's nuts. The building and the design is going to be great. So.
Any more questions? We still have time for a few more questions. No? Well, thank you so much, speakers today. I mean, it was a great presentation. Looking at this presentation, I want to go to that school back. So, with this, I would just like to conclude our today's AI section. Thank you all for being here. Again, just to let you know, since a lot of you were not here earlier, AI data is relatively new on the issue. If you guys want to get more involved, feel free to let me know or get notes. And again, I would like to thank all our speakers and with the vendor partners and Alpha Consulting Engineers for this great presentation over here. Let's give them a round of applause.